Good evening, everyone. Myself, Gautam Sharma. I welcome you all in a Sapience education. So today I am going to discuss about the Poisson ratio, lateral and longitudinal strain, elastic potential energy. Okay. So this is part third video, and two video I have already covered of this chapter. So the chapter which I am going to discuss is your mechanical properties of a solid. Okay. Mechanical properties of a solid. So before that, you need to understand that what is Poisson ratio. Okay, what is lateral and longitudinal strain and elastic potential energy? So I will discuss all this thing in step by step. So let us consider here Poisson ratio. Before you know that whenever see here, whenever this try to see in the picture, whenever you try to pull this object, so what will happen? Its thickness will decrease. So as strain is or change, strain is what? Strain is your change in length by original length. So in lengthwise, in this direction, there is a increase in the length. So suppose there is an increase in the length of change del L, and earlier the original length was L. So strain produced in this side is your longitudinal strain, because it is being, this type of strain is developed in the direction of the applied force, applied pressure. Now at the same time, what is happening here? What is happening? See, diameter of the object is get reduced. So earlier it was like this. So after that, what happened? Diameter of the object reduced. It means that the part in which we are not applying a force, or past rest of the on that axis, there is a decrease in a change in a length or change in a diameter. So there is also a strain, and this type of strain is known as lateral strain, where there is a change in diameter by original diameter. So earlier original diameter was like this, d. Now the diameter is what? D minus delta d. Delta means change in diameter, right? So this is what known as lateral strain, and the longitudinal strain will always involve in the direction of the applied force. Okay, and the rest part is known as lateral strain. Okay, so let us define Poisson ratio. So Poisson ratio is what? Poisson ratio, it is the ratio of lateral strain to the longitudinal strain. Okay, so what is lateral strain? Again I am telling you, the strain developed just rest of the part. See here, you are considering this part. So in this part we are applying a force. Then this axis or any other axis, for example, there is a three axis, x, y and z. Okay, so if you place an object, so this direction is your x direction, and this the above direction is your y direction, and this direction is your z direction. So if you apply a force on x direction, or force or any pressure is applied in x direction, so the strain developed in x direction is known as longitudinal strain, but the strain developed in y direction or z direction is known as lateral strain. So here the ratio of this lateral strain by longitudinal strain is called Poisson ratio. The side along the applied force is called longitudinal side, and the other than that is called lateral side. So I hope you have understood now Poisson ratio. So now if you want to derive how this Poisson ratio's value will be derived, see here. So first of all, tell me what is the longitudinal strain. See, longitudinal strain. See here, the strain. See here, this side force is being applied. So the change in this side, earlier length was L. Now after applied force, its length become L plus del L. So what is change in length? Del L. And what is original length? L. So longitudinal strain will be del L by L. Now I am talking about lateral strain. So as we talk about lateral strains, what is there? Earlier its diameter was d, but as soon as you stretched it, so its diameter reduced to d minus delta d. So what is the strain? Delta d by d. but the delta D is negative because it is being reduced, so we need to put here minus delta D by D. Now what is now Poisson ratio? This is what Poisson ratio we are talking about, Poisson's ratio. So Poisson ratio is your longitudinal strain by lateral strain. Sorry, lateral strain by longitudinal strain. So our lateral strain is minus delta D by D divided by delta L by L. So finally we are getting delta D by D into delta L by L, and this is your pure number. Okay, no dimension, no meter, no any units are there, only pure number is there. So for this you are getting a pure number at all. So this is what about Poisson ratio is. I hope you have understood now Poisson ratio. Now let us go for a values of a Poisson ratio. So what is the values of a Poisson ratio? So values of Poisson ratio depend upon the nature of the material. What type of nature of a material it is. Theoretical values of a Poisson ratio lies between -1 to 0.5, but actually practically most of the material have this value, that is it is greater than 0 and less than 0.5. And for general case of steel, it is for 0.2 to 0.30. Just you remember this. And the aluminum, for aluminum Poisson ratio is 0.33. So these two should be remembered by you. Okay. So I hope you have understood this Poisson ratio, right? So it is time to go for our next topic. Very important topic, that is your elastic potential energy in a stretch wire. Okay. So before that, I want to explain or make you clear. Let's see. Let us take an example. See here. So this is a rod like this, and it has having length L. Okay. So it is stretchable. Okay. Okay. Or you can say that this is a regular spring. You can take example of a spring also. Similarly, I will take as a spring here. So let us consider there is a spring like this. Okay, normal spring. There is a normal spring. So in both the case, if you apply a load, so what will happen? If you apply a load, what will happen? Or load L or any type of force if you will apply, then what will happen? It will get stretched. Its length will become L plus del L. So it means that it's stretched up to this. That is change in length is delta L. Or this spring will be observed like this, right? This spring will be observed like this, right? So it means that earlier it has a length L. Now it has length L plus del L. Okay. So can we say like this? So now tell me, if you release this spring, what will happen? Release this spring, what will happen? So it will go up, that is it has some energy. So as soon as you have applied a force or applied a load, so you need to do a work to get it stretched or to make it stretch. So as soon as you have stretched, it means that you have to do work. So your work got converted into potential energy. And as soon as you leave this, so this potential energy gets converted into kinetic energy, because as you leave, so a spring will move up and down like this. So it means that you need to do work gets converted into potential energy, and potential energy gets converted into finally kinetic energy. So now the thing is that how much potential energy is being stored in any stretched wire. So it means that if you will find work done, it means that you will able to find potential energy, because work done is the same as potential energy. Whatever you will do work on the work on stitching the wire, that work will get converted into potential energy at all. Okay. So let us discuss step by step. So I think you have understood the meaning of a potential energy, how we can stage. Or you can take an example. You have a toy. Suppose you have a toy and it has key. So you just move key like this, so that your energy or your work gets converted into potential energy. And as soon as you leave, so this potential energy gets converted into kinetic energy of the toy. So I hope these are the example from where you will able to understand how you need to find potential energy. So definitely for finding a potential energy stored in an elastic stretch wire, you need to find the work done on the stretch wire. So from this here, you let us see here. Let us see. This is an area of cross section, and this is a rod of length L, right? Now, if you apply a force F, so what will happen? Its size will increase, and its size increased from L to here. Change in length is L. That is, small l starts from 0. Earlier, before starting, l has a 0, l has a value 0, and after stage, its l become L. Okay, length become L. Okay, so length of the wire, that is original length, is your L, and small n, L is your change in length, and area of cross section is your A. And now tell me, what is the stress developed in this? So stress, you know that stress is equal to force by area. Now you know that what is the strain value. So strain has a value change in length. This is your change in length, and this is your original length, Now as you know that Young modulus of elasticity, it is your Young modulus of elasticity, and this is equal to stress by strain. So how much it is stress? F by A, and how much it has strain? L by small l. So finally, from this equation you can write force is equal to Young modulus of elasticity into area into fixed length by change in length. Okay, so this is very important equation. You should remember this, YAL by original length. Now next step, what do we need to do? Now let the wire has been stretched by DL length. See here, let us suppose that I have stretched it for a small length DL, not L. Just DL length has been stretched just for a small length. So when you stretch it, so you have to do work dW. It means that you have applied an energy. Now can we find how much this work is? So as we know that dW work is equal to F dot dl. So as the direction is same, so F dot dl has a cos theta is equal to 0, because you know the formula of work done is equal to F as cos theta. Here theta is equal to 0. Why? Because displacement and applied force has the same direction. So can we write here dW is equal to F dot dl. Now total work done in stretching wire. Now from L to L equal to 0 to L equal to L. See here, L is equal to 0 to L is equal to L. Means length is equal to final L, small l. Okay. So can we integrate it? So if you integrate, so you will get total work done. So can we write here total work done dW is equal to F dot dl, where force is what? Just now we have found force is equal to YAL by L, YA into small l by AL. So can we write here YAL by L into DL, and its range from, that is length varies, that is DL varies from 0 to L. So as you make it vary from 0 to L, so you can write here like this, YAL DL 0 to L. So now tell me, Y is Young modulus of elasticity, A is the area of cross section, and L is the length. So we can assume that area will be remain same approximately. So if you assume this, so YAL is your constant, because L is the original length will be constant. Now what is variable? Small length is variable, because see here it is starting from 0 to L. We don't know the values, right? So now you know that integration. So LDL, integration of LDL is your L square by 2. L square by 2, and you put the values 0 to L, so you will get YAL is YAL into L square by 2 only. Okay. So you have got this work done. Now tell me, I have just explained you that whatever you will do work, your work will get converted into potential energy. So can we tell that the potential energy, this work done on a wire has been converted into the potential energy of the wire? if you have earlier no energy at all, potential, no energy of the wire is there. But when you apply the force, so what happened? It has been stretched for this length. So as you stretch for this length, so what is happening here? So what is happening here? So you store some, you have to do work, and your work is being converted into potential energy of the wire. So finally, potential energy of the wire is equal to work done on it, that is equal to YAL by L square by 2. Now can we write here YA L square by capital L whole square into AL, because L multiply L here also, multiply L here also. So what you are getting? A small l by L, capital L whole square by into AL by 2. So as you know that L, that is change in length, by capital L is your strain. It is known as strain. Earlier I have already talked many times. I've talked in the all three videos, two previous videos. So can we put here half into Young modulus, that is y is your Young modulus of elasticity, and into change in length by original length is your strain square into volume of the wire. Okay. Now tell me, as you know that stress is proportional to strain, or stress is equal to Young modulus of elasticity into strain. So can we y into strain? So here Young modulus of elasticity into strain, one of the strain we can take here. So can we write here y into strain is equal to stress? So y is, this is your y, this is your strain. So can we write in place of y into one strain? See here, it is your square terms. So it has to so one strain you will take, then you will get stress. So can we write here in place of, see here, just I will again break for you that 1 by 2 into Young modulus of elasticity into strain whole square means strain is to strain into volume of the wire. So strain into Young modulus of elasticity is known as stress, just as I have shown you by derivation. So in place of this, so can we write it half into stress of the material into strain of the material into volume of the material. So just what I have written this. So I hope you have understood now. Now can we take this volume down? So potential energy of a wire divided by volume of wire is equal to stress into strain. So now U wire, that is total potential energy of a wire divided by volume of wire, can we write like a small u of the wire? So that is elastic potential energy per unit volume of the wire, and this is equal to half into sigma into strain. So this is the formula you need to understand, right? Okay. So I hope you have understood now the derivation part, and I have already provided notes. So go through the notes again and again. If you have any confusion, go through repeatedly. Go for repeat your videos so that you will able to understand this method. Okay. So I hope you have understood now. Now there is another topic, that why we have studied so many things, so many hard works we are doing for remembering this elastic behavior and all. What is the use? The most important use is the metallic parts of the machinery are never subjected to a stress beyond the elastic limit. So suppose here you know that elastic limit is your 900 Newton per meter square. Beyond this, if you will give, so wire or machine part will break. So we need to design a machine in such a way that it won't go for breakdown. It means that we don't put much load. For example, you have constructed a bridge. It has capacity of only 100 Newton per meter square. So what will happen? After that, after you apply a heavy traffic, so it will break down. So bridge is also being designed in such a way that we have to think that most heavy, it can withstand most heavy traffic. Thickness of road for a lifting heavy load. So here, for example, there is a heavy load like this, and you have a rope like this. So if you lift load with the rope, so rope will easily break if we don't design it properly. So for designing purpose, we need to understand what is the elastic limit of the rope, or we can make the thickness of a rope much more, so that it can withstand, and it must be of economical also. It is thickness means does not mean that you have made too much thickness, so it may be a costly and no use at all. Okay, so this type of application is there. Again, there is a bridge are designed in such a way that they do not bend much and break under the heavy traffic. Suppose bridge is designed, and if there is a heavy traffic and bridge will break down, so what will happen? Or bridge will bend, so there will be a lots of problem. So to avoid this problem, these designing procedures must be followed. Designing method or elasticity, we need to understand the material property at all. It is also used for designing beam. So many beams are there in wall beam like that, column structures are like that, building structures are like that. So many buildings are there. So we need to design the column thickness and all, so that it won't crack. If it will happen, so every day you will find that every building is cracking and all. So some accident will happen. So to avoid this accident, these concepts are used. So for example, here you can see that deflection of a beam. Suppose there is a beam and deflection of beam is given by W, that is load into L cube divided by 4 into BD cube into Young modulus. So if we have to design in such a way that deflection should be minimum at all, right? So if you are increasing load, it means that you have to increase the Young modulus. Also, see here, beam has a structure. Suppose this is your B and this is your D. So the ratio of BD should be calculated in such a way, and load should be calculated in such a way that its bending should be minimum. Minimum is 0.000 like this. Okay. So for this purpose only we have to use. So if you must remember this formula, deflection of beam. This is known as deflection of beam. This is known as deflection of beam. Okay, and this is equal to W, that is your load, into L cube, that is your length, by 4 into BD cube into Young modulus of elasticity. W is your load, L is your length of beam, and B is your width of beam. So if you are talking like beam like this, okay, so this is the B, and D is the depth of the beam, height of the beam, depth or height we can't say, thickness of the beam you can say. It is better to write thickness of the beam. Okay, so it is a thickness of the beam, okay. And why is here Young modulus of elasticity? Young modulus of elasticity. Okay, I hope you have understood now. Now by using this formula, you must give the values of such a that, or you want to design, then if you want to design, then how much length it should be there, or how much D should be there, how much B should be there. Just you put the value of deflection. For example, you just told an engineer that our beam deflection should be 0.001 meter. So put this value and you will get all the result. And you will also tell that I will put a load of 100 peoples, 100 truck, 100 bus. In this way you will able to design the beam at all. Okay, so see here, different cross sectional shapes are very important for here. So you can see different type of shapes are there. So shapes, why this type of shapes are used? So that it can withstand the maximum load at all. It is known as buckling. You know buckling? Buckling is what? It will bend. So we need to design in such a way that it won't buckle at all. So if it will buckle, there will be a lots of deflection and lots of problem at all. So I hope you have understood the application of the elasticity. I hope you have understood this chapter. Hope, and if you want more details, go through all the 3 videos whatever I have covered. Go through all the 3 videos, part 1, part 2 and part 3. If you have any problem, you just ask me in the comment section below. You can also download our notes. I have already given a link of the notes. So please download them, go through that notes, and do. I hope you have understood these things. And from next video, I will also come up with the special numerical, inside numerical, NCRT numerical at all, so that you will able to gain all the concepts. Thank you for today. I hope it's enough for today. Thank you everyone.